finish. If not sure if I can finish today. Like if not, we'll use tomorrow lesson to go through that a little bit more. So before we start the next exercise, just a little bit revision from implicit differentiation. So we really rushed through that yesterday. So find the equation of the tangent to the curve. Okay, give you the curve at the point 4, 1. So this is a point on the tangent already. What else do I need is dy dx at that point. Okay, so again, if I want to find tangent, I need the dy dx at that point. So what we'll do is we try to differentiate this equation here. Okay, if you want to differentiate that, so we diff the 2x squared, that just gives you 4x. And then if you want to differentiate minus 6xy, so what I'll do is I'll take the minus 6 out, like that's the coefficient, and I'll differentiate x times y. Okay, so x times y, if you differentiate x first, you get 1, and then you times v, so u dash v. And then you will have u v dash. So v dash, y will be the v. So you dy dx of y, you get 1 times dy dx. So because you differentiate y, you will times the dy dx. And then plus the 2y of dy dx. And that equals to 0. So we can just, that's minus 6y and minus 6x times dy dx plus 2y times dy dx equals to 0. So what we have on this side is 6x minus 6y equals to bracket 6x minus 2y of dy dx. So dy dx equals to 4x minus 6y over 6x minus 2y. And you can further divide 2 on it. So 2x minus 3y over 3x minus y. I divide 2 on every term. So 2x minus 3y over 3x minus y. So I want to find the gradient at the point 4, 1. So when x equals to 4 and y equals to 1, my dy dx equals to 2 times 4 minus 3 over 4 times 3, 12 minus 1. 3x 12 minus 1. So that's 8 minus 3, which is 5 over 11. Okay. Any questions up to here? No. Okay, so if you can find dy dx expression, just sub the value in. Okay, if I'm not substitute the value wrong. So substitute the value in, we get the gradient at that point, and we have y minus y1 equals to gradient x minus x1. Okay, so y minus y1 equals to gradient times x minus x1. So y equals to 5 over 11x minus 20 over 11 plus 11 over 11. That's 5 over 11x minus 9 over 11. Okay, that's the tangent. This, I think I still want to emphasize, do not forget to differentiate the constant as well. Differentiate the constant equals to 0, so do not forget the 0 there. Like I see students put 9 there and they get a completely different answer. So this is something needs to be aware of. Otherwise, like nothing really I need to talk about from this topic. It's just when you remember when you differentiate y, you need to put dy dx after that. All right, so just put your notes away. Okay, so about this page, like page 20, you don't need to worry about that too much. It's just like a really special method. It's not really in the study design. It's just something can give you, like, you can think about it and see if you can figure out a way to do it. So basically, is like for the whole page, the idea is if you log both sides and then do the differentiation on both sides, you get the same result. Okay, you can simplify that a little bit. So for example, the expression here is really complex. What we can do is we can log both sides first and think about what we can do for log. When we times inside, we plussing it. When we divide inside, we minus it. So we can make them all becomes plus and minus relationship. You don't need to use chain rule or quotient rule again and again. So which can simplify your calculation. That's the key idea. So basically I'm log both sides and then find the differentiation. It will be the same result. Okay, so this is about this whole page, but you don't need to know that. Okay, this is not something, it's not something really in the study design, but we can use this method to simplify our calculation. It's just like interesting page for you to think about. It's not really something important. All right. Before I start the graphing, graphing page for you today, I just want to show you what, I'm not going to do this question with you, but I'll just show you this is the part 1 exam from last year. Okay, this is the part 1 exam from last year. So look at this equation. You haven't really learned this function. Okay, this is not some function you're familiar with. So what we need to do here is, so you can see from last year's exam, they just give you a function you haven't really learned. This is a rational function. Okay, this is what we're going to learn today. But you don't know the rule for it. Like you don't know, this must looks like a truncus, not looks like a circle. You don't know that. You can't predict it. So you need to have the ability to deal with unfamiliar like functions, like how to sketch unfamiliar functions. So this is what we're going to talk about today. So when you see a function, you don't know what's the shape, what's the steps you need to take. Okay, so what's the steps you need to take? And you can see it's really relevant to the exam. That's why we use like 2 lessons to talk this like topic. So you won't get exactly the same thing I give you today, but what you need to learn today is more the ability to sketch unfamiliar functions, and the steps are all the same. Okay, the steps are all the same. All right. Okay, first of all, the functions we're going to sketch here is, okay, so these 3 pages, okay, I give you really colorful graphs. Okay, so the function we talk about here with a formula like that. Okay, so we have a times x to the power of n plus b over x to the power of n. Basically, it's a whole part plus a fraction. Okay, this whole part can be a linear, like because m can be 1 or 2 and n can be 1 or 2. So what we have is basically we have a linear there or we have a quadratic there. And we plus the fraction. Okay, the fraction, the top is a constant and bottom can be a linear or it could be a quadratic. Okay, so it's a quadratic plus a denominator with linear or quadratic fraction here. So power is either 1 or 2. Power is either 1 or 2 here. Okay, so this is this type of function, and I summarize all the shapes for you. I'm not requiring you to remember them. Okay, so more we talk about is how we sketch it. So first of all, you need to know is the non-vertical asymptotes. Okay, so we need to have the ability to figure out the non-vertical asymptotes. Okay, so what's the vertical asymptotes for this type of function? What 0? X equals to 0. So the vertical asymptotes is always x equals to 0. Okay, it's same for all the function because denominator is x to the power of 1 or x to the power of 2. Denominator can't be 0. That's why you have x equals to 0 as your vertical asymptotes. Well, except if we have translation. So, for example, x plus 1 to the power of 2. So the asymptotes will become minus 1. But let's think about transformation. If you just think about the most original graph, just the x there, we have vertical asymptotes at x equals to 0. Okay, so what's the non-vertical asymptotes? Okay, this is the special thing. This part will become the non-vertical asymptotes. Okay, so it doesn't matter what's here. Either it's a linear or quadratic, that will become the next asymptotes. Okay, that will become the next asymptotes. Because, okay, the reason is this will never equals to 0. Okay, this whole fraction here will never be 0 because the numerator is not 0. How to make a fraction be 0 is the numerator 0. 0 divided by something equals to 0. So it doesn't matter how you change the x value, this part is just not going to be 0. Okay, so if that's what, but it can be approaching to 0. Think about if your x is really big, really big. So this thing is approaching to 0. So the y value is actually approaching to this value. So that's why this part will become asymptotes. Okay, this part will become asymptotes. So that's something we need to be aware of. And then, okay, I'm not going to talk about the graph one by one. So let's just move to page 3. Like we have some space here. Okay, so use that space to think about what we need to find when we sketch a familiar graph. Okay, a couple of things. We don't need to really talk about things in order. But first of all, what we will think about, if you give you a graph and ask you to sketch it, what's the thing you may be interested in? What are you trying to find? Yep, x, y, intercept. That must be something we're looking at the beginning. Well, before like we start year 12, like year 9, year 7, we find x, y, intercept for any graph. Okay, so first is x, y, intercept. Okay, second thing, what you may think about. Asymptotes, yep. So when you will have asymptotes, like in what situation? Well, the one I just talked about, the whole part will become asymptotes. But what else? Like, how do you find x equals to 0? Like the vertical one. Undefined. Okay, so denominator equals to 0 gives you vertical asymptotes. Like hyperbolas, you have horizontal one, like the most original one. But think about the non-vertical one as well. Okay, the non-vertical asymptotes, well, that one you need to remember because it's showing you this either the linear part or the quadratic part, you will have that asymptotes. Okay, so think about denominator equals to 0, that will give you the vertical asymptotes, and think about the whole part, like except the fraction, the other part will become the non-vertical asymptotes. Well, think about any horizontal one, that will be the regular one, like rectangular hyperbolas, those horizontal ones. What other things you may be interested in? Turning point or stationary point of inflection. So what we need to do for that? Yeah, so f dash x or dy dx equals to 0 to find stationary points. Okay, find the coordinates, give the coordinates, because I need to know where that occur and also the nature. That is a maximum or a minimum, that will affect the shape. Okay, that will affect the shape. So give the coordinates and also give nature. Not enough just say x equals 1, x equals 2 is the stationary point and like not working further. So you need to test nature. So test nature, I can use second derivative. Okay, second derivative, I can test nature by using second derivative. Second derivative is greater than 0, minimum. Second derivative bigger than 0, smaller than 0, maximum, equals to 0, test the sign change, stationary point of inflection. Okay, so test nature. Well, you may be asked to find point of inflection as well. Depends on the question. If question didn't say that, like you don't really need to worry about it. But if question says like find a point of inflection, we need to use second derivative equals to 0. Okay, and test nature and sign change. Okay, and think about sign change. What other things you may think about? The behavior of the graph, like how do you think about behavior? Like others go to infinity, like really quick, or like in a slowing way, like increasing, or like it's really fast increasing, or it's approaching to somewhere. We need to think about when x approaching to infinity, well, if possible, or x approaching to negative infinity, what y looks like. Okay, how y behave when x go to infinity, x go to negative infinity. Well, sometimes we have asymptotes there. We can't really go infinity. But like if possible, we will think about the behavior for when x equals to positive infinity, negative infinity. And also when x approaching to asymptotes. Okay, so when x, well, say if we have asymptotes at x equals to 2, then think about x approaching to 2 and x approaching to negative from the other side. What's the behavior in that case? Okay, so what y looks like in that case. Okay, so think about the behavior. Well, you won't have all of it, okay? You won't have all of it. But like if you can consider all of this, you will like really like close to actual shape. Like turning point, this step is a very important thing. Like that really gives you instructions what's happening. All right, something needs to be careful with. Say when you solve the first step, you don't have xy intercept. So you need to pay attention. When you sketch your graph, you can't create xy intercepts. So in some, even though you haven't solved out xy intercepts, but to an extent, it actually tells you where your graph can exist. Like say, for example, you can't going down in this way because you will touch x-axis if you don't have x-intercept. So your graph must turn back to going up, so not going down because you can't touch x-axis. So if you can't solve out xy intercepts, it's actually telling you where your graph can exist and how the graph should go. Okay, we'll just like finish here. Like we'll see a couple of graphs and then come back to decide if there's more things we can add on this checklist. So if we before that, you step 0 maybe if the power of top is higher or equals to the bottom, we need to go long division first. That's something I forgot to talk about. If the power is equal or greater on the numerator, so the degree of the polynomial is equal or greater than the bottom degree, then we need to do long division. Okay, so think about the power thing. We need to go for long division. Or if there's any other ways you can quickly get it done, that's fine. Okay, so by knowing that, can you go to example 1, please? Okay, we should go for long division, right? Top is a cube and bottom is a linear. So we need to go long division. But like in this case, I don't really need to go for long division. Like I can really get the answer quickly. So fx equals to x squared plus 12x. Like you can do long division if you want, but I can really get that quickly. This is one of the equations I was talking about before, right? So when asymptotes, you can see x equals to 0. So I will sketch this one. I forgot my ruler. Wait, are you surprised that x equals to 0 or the ruler? The ruler, okay. One of the students tell me. It's just there. It's okay. Technology. Okay, what's the other asymptotes? Y equals x squared because 2 over x won't become 0. So x squared, okay, x squared. X squared, I'll have 0, 0 here. 0, 0. Label it accurately. So we have 1, 1, 2, 4, 3, 9, 3, 9. So that's asymptote. So make sure you have dot lines. Okay. That's the asymptotes. Y equals to x squared. Okay. Okay. So what else you want to look at? Like follow the steps. What's step 1 we talk about? Well, we skip to step 2. What's step 1? y-intercept, right? Can I have y-intercept? No. Okay. Can I have x-intercept? Yes. So how to solve x-intercept? Which equation you use? Do you use the original one or use the like after factor? Like, it makes a difference. First one, if you make the numerator equals to 0, the whole function will be 0. It will be much easier to solve. If you use the second one, you need to make x squared equals to minus 2 over x, and then you need to change the x to the other side and then cube root that. So if fx equals to 0, you only need x cubed plus 2 to be 0. Like, you don't need to worry about the denominator. Doesn't matter what's the denominator. If your numerator equals to 0, 0 over anything is 0. So x cubed equals to minus 2, x equals to minus cube root 2. Where's minus cube root 2? Like, approximately more than 1, less than 2, right? Less than 2. So a bit more than 1, so somewhere here. Minus cube root 2, comma 0. Label that, okay? So that's your x-intercept. And remember, you don't have y-intercept. Do not go back to the page to see what the graph looks like. Let's assume you just don't know the shape and you're trying to figure it out by yourself. So, yeah, do you know what asymptotes actually do? It actually cut the continuum plane into a couple of planes. Let's say that's one area, that's one area, that's one area, and that's one area. So cut the continuum plane into 4 different states. And then we have graphs in somewhere. Okay, so okay, what's the next step we need to do? What's the next step? So after we find x, y-intercept, after we find asymptotes, what turning point? Okay, to find turning point. So f dash x. Well, I may use the simplified one to find f dash x. So that's just 2x minus 2 over x squared is x to the power of minus 1. So minus 2 and x to the power of minus 2. So f dash x equals to 0. We have 2x equals to 2 over x squared. Okay, so what's that? X cubed equals to 1. Is it? Yeah, so we have x equals to 1. Okay, x equals to 1. What y equals to? So f1. f1 equals to 1 plus 2 over 1, that's 3. So coordinates is 1, 3. 1, 3. 1, 2, 3 is here. Okay. By just looking at this graph, can you tell me what kind of turning point or point inflection it could be? Minimum. It's not going to be maximum, right? Like, it's not going to going down because it's going to touch. But what I can do is I can just find f dash dash x. Just find f dash dash x. Well, you don't need to do that. If you can see that's a minimum turning point. If you see, okay, it's reasonable, the graph should have a minimum turning point here. Otherwise, it's going to touch the asymptotes. It's going to just go across the outside the parabola. So that's something reasonable to say. But if you're not sure about it, just test the second derivative. That's 2 plus 4, and that's definitely greater than 0. So this one is a minimum turning point. You can just write it here to make sure you know that's a minimum turning point. What other things do you need? We find, well, I don't really need point of inflection. Like, it's not asking me to find that. I can find it, but like, it's not really necessary. Yep, the behavior, like when it's go infinity. But like, I'm not sure if you can see that the graph is here and here. And because the asymptote is here, the graph in the end needs to approach into the asymptotes. So what we will have is oh, that's fine, that's fine. It's not a point of inflection, really. It's not a point of inflection. It's just a point. It's just like x-intercept. And it's approaching. It's approaching. Let's think about that. There's only one turning point, and it's here. And it's a really long turning point. The only way we can sketch the graph is like that. And it's not going to touch the asymptotes. It's not going to cross the asymptotes. So the only way we can sketch it is just that. And think about this. That's the only x-intercept we have. There's only one x-intercept. And the only way we can sketch it is like that. It's both ends approaching to the asymptotes. That's how we figure out the shape. Okay, that's how we figure out the shape. Yeah, it's important. Make sure you understand. Okay. Because there's no other turning point, the graph is not going to turn. There's only one x-intercept, and it only goes across the point negative cube root 2. Okay, so the only way we can sketch graph is like that. There's no other ways we can sketch it. Okay, so that's why we know the shape. Any questions? In this one, we don't need to consider the behavior when x go to infinity because the asymptotes already bound the graph into that region, and that's how we can sketch it. I'll tell you when we need to test the x approaching to infinity thing. It's like in the later on exercise. Okay, we'll draw another one. Okay, let's look at example 2. What we need to do before we start sketching it? Simplify it. How to simplify that? Yep. You don't need to do long division. It's a single x. Oh, sorry, 6. What do you guys say about this function? Okay, so this one, like I don't have an ax, we have an ax minus 6, but it's the same logic. This thing can't be 0, so it will become the asymptotes at x minus 6. So your x minus 6 will be the asymptotes. If there's a single x, then x will be the asymptotes. So it's the same reason. It's just a linear there. Then that linear will become your asymptotes. So you hide the fraction. Whatever left is the asymptotes. So we have asymptotes at x minus 6. So x minus 6, we have 6, 0 and 0, 6.
Oh my God.
Oh, it's x minus 6, sorry. 6. X minus 6, so minus 6 is here. It's here. And here. This way. Why are you so surprised by this ruler? Okay, so x minus 6 here. What are the asymptotes we have? X equals to 0. So again, you two asymptotes separate the graph, like the Cartesian plan, into 4 different areas. Okay, what else we need? What's the x-intercepts? 3. Okay, so we have x-intercept at 3. Is that the only one? Yeah, okay, that's the only one. So what else we need to find? There's no y-intercept. Turning point. Okay, let's find turning point. So that's 1 minus 9 over x squared. That's the derivative. And when derivative equals to 0, we have 1 equals to 9 over x squared. X squared equals to 9. What x equals to? 12 minus 3. Good. So what's f3? 0. So f3 equals to 0. So it's actually this point. This point is x-intercept and the turning point. And what's f negative 3? So it's negative 3 minus 3 squared over negative 3. So negative 3 and negative 12. Okay, what do you think the graph will look like? It's like a tick, right? It's like a tick. So it's very, the scale is not very nice. Yeah, so it's just touch the x-axis and then going up, and then go approaching to that. And the other one will be this way and this way. The scale is not very good, but like you can see, the graph should be like a rotated hyperbola. Well, like there will be 16 different combinations between linear and quadratic fractions. So like a fraction denominator is linear or quadratic, and the integer part is linear or quadratic. There will be 16 different combinations, and you have 16 different graphs. But all the graphs will be sketched by the same way. You can find enough practice on your textbook one by one, like you can try them. But I'm not going to keep sketching this type of functions. I need to move on to the next one. So we'll have a rest first, and then if you still want to do something, could you please think about the reciprocal function? Okay, think about reciprocal. We learned reciprocal last year, right? Did we? Reciprocal. Yeah? Well, I don't really mind to remember or not, but have you learned it? Like, do you have a little bit like remember of it? Yeah? Okay, good. Then read through the table and think about what we have done. Well, I can't go very detailed. I will sketch two reciprocal function with you, and then we need to move on to the next. So read through that, have a brief, and then start of next period, we'll come back to this question.